Hello everyone, here we'll be discussing chapter 8.4, which is about vectors and dot products. Now the dot product is basically a way for us to somewhat try to devise a multiplication rule for vectors. Now the addition rule we found for vectors was a pretty intuitive one, and remember this is all definition, so it's just things we're kind of making up that should kind of make sense to us, and they also have some type of geometric consequences like we saw for adding vectors. It's just connecting the most endpoints to create a new vector, kind of. Now for this dot product, it's hard to understand what this really represents. It actually represents the area of the parallelogram that these two vectors kind of embody. So if you consider the vector u and the vector v, if you kind of duplicate u and v to make this a parallelogram like this, so this is a copy of u, this is a copy of v, the area of this parallelogram ends up being this value. So if we let u be the vector in component form u1, u2, and similarly v is v1, v2, then the dot product of u and v we define to be u1, v1 plus u2, v2. Now something to notice here is that this is a result involving numbers only. In fact, there's no components really here. In other words, this is just a scalar. So this is a scalar quantity. So the result is a scalar. It's not a vector itself. So that's pretty important to note, I think. And from this definition, we get a few consequences, some properties, kind of like we got for, for scalar multiplication for addition, but there's not that many. And they're pretty intuitive. They kind of are easy to show, but they're based, again, on this definition. They're consequences of the definition. So the first one is commutativity. If you take the dot product of two vectors in any order, you get the same result. If you take the dot product with the zero vector, you get the zero scalar, so the number zero. Dot products are distributive over vector addition. So u dot v plus w is the same as u dot v plus u dot w. And if you dot a vector with itself, you actually get the magnitude squared. That's actually not too hard to show, and we'll kind of see that in an example, actually. And then this property here says that there's associativity with vector dot products and with a scalar multiplication. Now the one thing that I don't have written here, of course, is associativity with dot products. And maybe you can convince yourself to see if that's true or not. I'm not going to bother with it because it's a little beyond what we want to discuss, but it's just an interesting thing to think about. And I don't think it'd be too hard to show if it's true or not. Just create a new vector, u1, u2 is is u, v1, v2 will be v, and then w will be w1, w2. And then if you take the dot product of those three, see if doing it in any different order will give you the same result. I think it should, just thinking about it. But anyways, these are the ones I want to focus on. Now, first off, for these examples, I'll just be using the definition that we've described here with the dot product. And then afterwards, we'll look at some examples that will involve some more advanced notions that we can basically apply the properties to. But anyways, let's get right to this. So this is fairly straightforward. Basically, all we're doing is multiplying the first two together, added to multiplying the second two together. So you should kind of pair them up like this. So this is just 4 times 2 plus 5 times 3. So it's 8 plus 15. So our answer is 23 here, and that's it. Awesome. So similarly for this one, we have 1 times 2, which is 2, and then negative 1 times 2, which is negative 2. You add those, you get 0. So I did that a little more quickly, of course. And to be quite honest, these dot products are not that difficult to compute. So at some point, they're kind of one-liners. So here I showed detail, here I showed some detail. Here I'm not going to show anything. I'm just going to do it in my head. 0 times 4 is 0. Let me single underline that. And then 3 times negative 2 is negative 6. 0 plus negative 6 is negative 6. So that's how easy it can be to find the dot product of two vectors, multiply pairwise, and add those results. And notice our results are scalar numbers, not vectors themselves. And notice it's actually possible to have two vectors whose dot product is 0, and these are actually known as what are called orthogonal vectors. Now the word orthogonal essentially means that orthogonal. Now, the word orthogonal actually means that they differ by 90 degrees. It's what orthogonal is trying to say. And in fact, this is true if two dot products have or two vectors, I should say, have a dot product of 0, then they actually differ by a 90-degree angle. And we'll see this amongst other things in a bit, but first let's see some examples involving these properties now. All right, so for this example, we're given u, v, and w, and we're asked to find the following. The first thing I want to say before we begin, though, is what I said earlier about the parallelogram being equal to the area of that parallelogram being equal to the dot product is not necessarily true. There's still a relationship between them, but it's not exactly equality. In fact, if you want to know what it is, really, it's the dot product multiplied by tangent of the angle in between. We may talk about that in a little bit after doing this, because we will be discussing the angle in between two vectors as a consequence of dot product, as it turns out. Of course, tangent of 90 degrees is actually undefined. So with that being said, when the parallelogram has an angle of 90 degrees, you'll end up getting a rectangle in reality, which the area would be pretty easy to find because it's just base times height, but in fact it's always base times height. Well, anyways, yeah, that again, I'm going a little bit on a tangent there. But you can look into that if you like. There's a nice relationship between them, and we may discuss it in a bit. The next thing I wanted to talk about is actually to do with this problem here. So I had mentioned that what was not on the list of properties was associativity with dot products. And associativity with dot products cannot exist. And the reason why is basically seen in this example here. We have the dot product of these two, but then there's no dot in between this vector and this quantity here. And the reason being is that this is a scalar, and a scalar can't be dotted to a vector. Only a vector can be dotted to a vector. So for that reason, associativity can't even be a thing, because once you dot two vectors, it's no longer a vector anyways. So I hope that clears some things up. But let's get to this. So u dot v, I think we can do right away. Multiplying -1 to 2 gives you -2, so I'll actually write it out to be a little detailed. And then multiplying these two gives you -12. And then we're multiplying this to the vector 1, -2. Which I know looks funny, but remember this is just a scalar. In fact, we can figure out what this is, -14. If you scale -14 in, you get the vector -14 comma +28. And there we are. Awesome. So that's the answer for part 1. Part 2, we could use a property here. We could say that this 2 we can actually pull out in front. Just the u dot v, which we already did, that's just a -14 in this case. So our answer must naturally be just -28. So again, we can just say this is the same as u dot v using one of those properties we saw. We know u dot v is -14, so our answer must be 2 times -14, which is of course -28, and we are done with this problem now. Now, if you wanted to do it the other way, of course, 2 scaled into this is 4, -8, and if you consider 4, -8 dotted with -1, 3, clearly you get -4, -24, those combine indeed to -28. So it's nice to at least see that both ways coincide. Now, third part here, we could find the magnitude the kind of, I guess, older way, where we look at the components of these, square them, add those, and then take the square root. But what I want to show you here is that, remember that this squared is equal to the vector dotted with itself. So that means the magnitude without the square is simply the square root of the vector dotted with itself. But now notice, if you take a dot product of a vector with itself, you get the first term multiplied by itself, which is literally squaring the first component. And then you get the second component multiplied by itself, and you literally get the second component squared. And the reason why this is true is if you were to write next to each other, -1, 3, -1, 3, when you dot those, you get -1 times -1, which is -1 squared, and similarly with 3. So notice, actually, we get the same exact thing we would get doing it the other way as well. So this kind of verifies that property that I was talking about earlier. And of course, this is just +1 and 9. Those combine to 10. A radical 10 is our answer. That cannot be simplified. Fantastic. So now we're going to move on to another idea. And again, it's just going to be talking about the angle in between vectors, and then we'll see where it goes from there. All right, so here's the main concept behind angles in between vectors. So we say if theta is the angle between the two vectors u and v, then this must be true of the angle between them. So cosine of the angle must be their dot product divided by the product of their magnitudes. Now this is not too difficult to show. It basically uses the difference formula for cosine. I'll try to explain a little bit off to the side here with a nice visualization. So imagine we have this xy plane, and we're given these two vectors u and v. I'm going to try to make this as quick as possible. Let's say u's here and v's here. So this will be, let's say v1. This is u1. Let's call it ux and vx. Maybe that's a little better. And then their projections on the y-axis we'll call uy, like that, and vy. Now their lengths are the magnitudes, but if we just call those u and v, then it'll be a little easier to see what's going on. But in reality, if you kind of imagine these angles are, let's say this angle is alpha, like that, and this angle of u to the x-axis is beta, let's say. So now if you take cosine of beta minus, well not cosine of beta, but if you take cosine of beta minus alpha, this is actually the angle in between u and v. Notice the angle beta minus the angle alpha is indeed the angle in between. Okay. Also notice that we have a formula for this, the difference formula of cosine. This is cosine of beta cosine alpha minus sine beta sine alpha. So that's essentially the proof here, that if you actually figure out what these are, it's not too difficult to do, and you end up getting this as a consequence. Because notice, the dot product is just ux times vx plus uy times vy. Now the x's are the cosines, the y's are the sines, is basically what's happening. Of course, you have to divide by their lengths, their magnitudes. So if you call those u and v, multiplying through by uv will give you a similar consequence, or I guess dividing through by uv. So it's a little, I mean, it takes a little finesse, but this is really the outline of the proof here. So I'm not going to go into details of the proof beyond this, but at least I've kind of given you a sketch here. So I think that's okay, because it involves very much the difference formula of cosine. So now getting into things, let's see if we can use this knowledge now, assuming that we're convinced that this is indeed the case. We can find the angle in between these two given vectors, and I think we can. So according to what we just saw above, cosine of the angle in between them, theta, is the dot product. So the dot product of these two is 4 times 3 plus 3 times 5, so that's 12 plus 15, divided by the magnitudes of the vectors. Now the magnitude of u, let's see, 4 squared plus 3 squared is 16 plus 9 is 25, so the square root of that's 5, okay, times the magnitude of this vector 3, 5 is 3 squared plus 25, so it's 9 plus 25, which is 34, so we get radical 34. So 5 radical 34 in the denominator here. So this ends up being, let's see, it's 27 over 5 radical 34. So this implies that theta is equal to cosine inverse of this value, 27 over 5 radical 34. Now all we have to do is use our calculator. I'm going to write our angle in degrees, so I'm going to be in degree mode, and let's see what we get. So my calculator gave me a value that rounds to about 22.17 degrees if we round to the nearest 2 decimal places. So I think that's okay. So I'm going to leave it like that. But again, yeah, it just uses the fact that cosine of the angle has to do with the dot product and the product of the magnitudes. So it's not too difficult to do, but again, to prove this is a little iffy. Anyways, now the next thing I want to talk about is this definition we kind of spoke about earlier, and that's the word orthogonal. So we say vectors are orthogonal when the angle in between them is 90, essentially meaning that they're perpendicular. So the phrase perpendicular and orthogonal are kind of the same. Only orthogonal applies to vectors specifically, or perpendicular just applies to lines. Now, since cosine of 90 degrees is equal to 0, then from this formulation here, that means this fraction is 0, meaning the numerator has to be 0, so that implies that the dot product is 0. And this actually is the other way around as well. So this is if and only if. So basically, long story short, orthogonal vectors have a dot product of 0. So now we want to determine here, these two, for this example, we want to determine if these two vectors u and v are orthogonal. And we can do that by, well, taking their dot product and seeing if it is indeed 0. So we end up getting 2 times 6, so I'll be a little detailed here. So u dot v is equal to 2 times 6 plus negative 3 times 4. Now notice, of course, this is just 12 minus 12, and that is indeed 0. So, of course, the answer is yes, they are orthogonal. Great. So now we're going to move on to some more advanced concept that will kind of piggyback off of this idea and will allow us to look at what are called projections of vectors from another vector. So let's take a look to see what that's all about, and then I think that'll basically be the end for 8.4. All right, so the last topic now that we're going to discuss in this section is vector components. It's a little kind of weird to think of, but basically components of vectors are usually the x-axis coordinate and the y-axis coordinate vectors. So that's what we often think of as components. But here, when we speak of vector components, we're kind of talking in a more general sense, where we can actually basically rotate the x-axis. And really what this kind of turns into is a discussion on a different base or basis of vectors, which I know sounds kind of funny, but it depends what you're projecting onto. So let's see if we can describe what's going on here. So let's let u and v be vectors such that u is equal to u1 plus, or w1 plus w2, where w1 and w2 are orthogonal, and w1 shares direction with v. So that means we're given two vectors, u and v, and we can actually see it like this. Let's say this is v, and this is u. Now I'm making it look like the magnitude is the same, but for all we know u is way larger than v. Let's make it look like it's a little smaller than v. So now what we want to do is kind of tilt our heads a little bit and consider this to be the kind of like x-axis coordinate. So what we're going to basically do is project this down and consider this kind of like our component. So our component here, this guy is going to be our w1. Now, the whole part about w1 sharing direction with v, that's basically what this says. They have the same angle. If v and w1 share the same angle, then remember that you can actually project w1, well, not project w1, we can flow w1 around until it lies completely on v because they have the same angle. Great. And now, since w1 and w2 are orthogonal, then we can create a 90-degree angle like this to get w2. And moreover, so let's just say w2, sorry. And moreover, since w1 plus w2 is u, then they should line up exactly like this, because if you float w2 over, then connecting tail of w1 to the head of w2 will give a diagonal of exactly u. So notice if you tilt your head, this kind of just looks like the x-axis and y-axis, but this is a generalization thereof. So I hope that idea makes sense. Now, we call w1 the projection of u onto v. We're basically looking at the shadow of u onto the vector v, so it's going to be a portion of it. Now, it could be more than it, depending if u is larger. But regardless, this is how we denote that projection. So it's the shadow of u onto v, which again, could be all of v, could be more than v, or could be smaller than v. Here it looks like it's smaller than v. Awesome. So now there are a few nice consequences, and let's see if we can find, in fact, there's really just one big consequence. So let's see if we can show that right now. So now I'm going to kind of go into proof mode a little bit and just, so I'm bordering this off a little bit, and I want to see if we can figure something out. So now u is equal to w1 plus w2, so let me write that. U is equal to w1 plus w2, and, well, w1 is what? w1 is, well, it shares direction with v. That means there exists some scalar such that w1 is equal to that scalar c times v1. Or not v1, but just v. There we go. We don't even have v1. Great. So far this is what we have. Now what? Well, let's see. So we know w1 and w2 are orthogonal, but what I want to do actually is I want to take the dot product of u and v to see if we can see something. So we take the dot product of u and v. Basically, I'm going to take the dot product of both sides, and we get u dotted with v is equal to this dotted with v, So CV plus W2 dotted with V. And now we can use some vector properties. Notice dot product actually distributes over vector multiplication. So this is, well, C V dot V plus W2 dot V. Okay, this is actually really good because actually, if you think about it, this really is the square of the magnitude of V from one of the properties we saw. Also, a V is what? What is V? Well, V is a scalar multiple of W1. In fact, we wrote it the other way around. We wrote that W1 is a scalar of V. But look, if W1 is equal to C times V, then that means we can write V as 1 over C times W1. And 1 over C is still a scalar, so that's okay, we can do that. In other words, we can replace V with 1 over C times W1. And now there's a whole lot of really nice things that happen. First off, we can move things around. This scalar can be pulled out like we saw earlier. And then we get W2 dotted with W1, which I'll write like this. And notice since they are orthogonal, this must be 0. And that's kind of it. We can actually solve for that scalar C now. So in fact, what we get as a consequence here, from all of this work here, is that the scalar C must be U dot V divided by the magnitude of V squared. Perfect. Now, what is so important about C? Well, remember that we said that W1 is V times C. So what that means is we can actually write W1, which is we call the projection of U onto V. So this is our actual big result here. Projection of U onto V, like this, is equal to, well, it's actually equal to, let's see, W1, which is this guy, is equal to C times V, but we found out what C is. So C is actually equal to this, U dot V, all divided by the magnitude of V squared. And notice this quantity here is just a scalar because C is a scalar, but multiplied by what? Multiplied by, of course, V, because W1 is C times V, this is C, and that's multiplied by the vector V. Let me just carefully box this. This is our grand result of all of this. This is basically how we'll be finding the projection of a vector onto another vector. It's the dot product divided by the magnitude of the one we're projecting onto, multiplied by that vector itself. So we'll do, I think, just 1 or 2 examples of this, and then that'll be the end for 8.4 finally. Right, so here's the last example we're going to take a look at, and we want to find the projection of this vector u onto this vector v. But then from there, we also want to write u as a sum of 2 orthogonal vectors, one of which will obviously be the projection. So let's get right to it, and let's find the projection of u onto v. So remember, the notation is like this, and our big discussion earlier led to the dot product of u and v divided by the magnitude of v quantity squared, or magnitude of v squared, and that quantity multiplied by the vector v. So now the dot product of u and v in this case is 18 minus 10. See that? So 6 times 3 is 18, negative 5 and 2 is negative 10. So this is really just 18 minus 10, which is, well, 8. Divided by the magnitude of v squared. And the magnitude of v is, remember, just squaring these and adding those and taking the square root of that. So if you square these, you get 36 and 4. That's, of course, radical 40. And radical 40 is 2 radical 10 because 4 is 2 squared. So really we just get this. But you know what? We want to square it, so really it's just 8 over 40. So this is the magnitude, but the magnitude squared is just 40 itself. So that's not too hard to see. And then now we're going to multiply this by the vector v, which is 6, 2. Now, of course, there's some cross-cancellation here, or not cross-cancellation, but cancellation. And we get 1 over 5 times this vector 6, 2. And if you want to scale it in, you can. You'll get 6 over 5, comma 2 over 5, and that's okay. But I'm going to leave it like that, I think. And this is what we call, remember, we call this W1. Now, to find W2, well, that I actually quite haven't shown you, but it's not too bad because since we know that W1 plus W2 must equal U, and that means W2 must be U minus W1. So really we have 3 comma negative 5. So this is the first part of our question, the projection part. That's the projection. The second part of our question requires us to find W2 and then finally write U as W1 plus W2. So we have this vector U minus this new vector 1/5 and 6, 2, but I'll actually scale it in here. So I got, in fact, let me scale in the negative 1/5 because the minus from here, we'll consider that as negative 1/5. So we get negative 6 over 5, comma, negative 2 over 5. And now finally adding these two vectors gives us 3 minus 6 over 5. 3 is 15 over 5. 15 minus 6 is 9 over 5. Comma, when you add these together, well, let's see, negative 25 over 5 is the same as negative 5. And then minus a 2 over 5 will give us negative 27 over 5. That's nice because we can actually pull out a 9 over 5 here, which is nice. So I think I'm actually going to do that. It's something we don't really have to do, but I'll just do it anyways. So we can actually pull out 9 over 5 from this. And what we end up getting here, yeah, because look, we could have pulled out a 2 in reality from here. So then we possibly could have seen some more relationship. But anyways, that's fine. So pulling out 9 over 5 gives us 1 comma negative 3. Nice. So now we can say U is equal to W1, which is 1/5, 6, 2, plus W2, which is 9/5, 1 negative 3. Now I think that's kind of nice that we can write it like this, but of course if you don't like this, you can scale them in, so you can write this as this vector with no scalar on the outside plus this vector with no scalar on the outside. So it just depends how you want to write it, but I kind of like the first one better. So this is my result for this. It's equivalent to this one, so you can box this if you want to. And, just to be safe, I'll box both of them. Which I know sounds kind of funny, but on an exam or something, I would tell you specifically how to write it. But at this point, they're kind of the same, and that simplification in my mind is a little not that important at this level. But anyways, there it is, and we kind of saw that, so that's nice. So again, that's all I wanted to say for 8.4. So now I'll see you in the next video for 8.5, and then finally 8.6, where we'll finish off chapter 8. It's going to be a lot of fun. Hope you enjoyed this. Thanks for watching, and I'll see you then.